Okay. So then let's start directly with my presentation about artificial morality and dynamic risk management for autonomous systems. And a similar presentation I already gave in another workshop, and I received good feedback, and I thought it's worth to share some of the thoughts here. And yeah, we'll be happy to discuss them with you, maybe also in follow-up meetings. So happy to receive some feedback here. So first of all, I want to characterize a little bit the approaches of dynamic risk management that we developed at Fraunhofer IESE, and then also talk a little bit about the relation to autonomous systems and why dynamic risk management for autonomous systems implies artificial morality. Without going too much into definitions and what this really is and means. So artificial, then that's why in the second part I will talk about fundamentals, some terms, and also different implementation approaches. And then I will summarize the current status about approaches and sketch an evolution of dynamic risk management for autonomous systems. So starting with conditional safety certificates, which was a pioneer, I would say, of dynamic risk management approaches. So there was already a PhD in 2014 from Daniel Schneider, who is also in the organizing committee and maybe also here as listener, or will join later. And the idea of this approach, or what it can do, it enables to implement a safety goal for an application which is realized by a system of systems or a group of cyber-physical systems. So for instance, the baling of hay here is realized by an implement and a tractor. So they work together to achieve this. And there you have the safety goal that you should not run over people, for instance. And this is something that has to be realized by both of them together, so both physical systems, because the implement will give commands concerning the speed and so on. But maybe, it's not possible to fully implement the safety function on the tractor. And therefore, you need some agreement between these systems. So it's a dynamic realization of the safety goal depending on the current sensors that your cyber physical systems provide and how they currently cooperate. Another example would be, for instance, in intralogistics, having shared perception and of AGVs, so automated guided vehicles. But there is not necessarily a need to estimate and assess risks during operation. So these models that we have here, which are somehow digital twins with dependability aspects, they can be at some point or at some level risk agnostic. And the idea is just to implement somehow or to formalize the safety element out of context approach and have some guaranteed demand reasoning concerning safety claims, so safety requirements. So you do a matching with respect to the content of the safety requirements and also the integrity levels. And this raises a little bit the question, is this matching of integrity levels really sufficient? And are there maybe other means to formalize the level of confidence in a safety claim? And this question also came up, for instance, when it comes to matching between integrity levels of different domains. If you think about that, one is developed with respect to the other one with performance level and so on. And one approach to deal with this is given by digital dependability identities. So they are the more general case. They enhance conditional safety certificates, and they are formalized assurance cases. So let me explain and elaborate a little bit on this. So an assurance case is an argument, includes objective constraints or a claim concerning objective constraints, an argument, and evidences on which the argument is based on. And this argument can be structured in a way that you break down the overall claim into subclaims, and you further break it down with reasoning steps until you can directly prove the claims with evidences. And while this reasoning, so this argumentation tree, you could have a lot of assumptions that you make explicit, maybe assumptions on input, on the context, and so on. And if you now look what confidence means, so the confidence in a top level claim, so that relates to the argument. And for instance, the number of assumptions that you have, and yeah, how plausible they are, how valid they are. So, and also the evidence that you give for this claim. So this gives you some means to assess the level of confidence. And according to this idea, DDIs formalize assurance cases so that the systems can reason about the confidence they get and to reason whether this is sufficient or not. And you can also support, for instance, your reasoning with fault models and yeah, whatever you created during safety engineering, the artifacts, and you make them executable so that you have on a higher level, you can combine these models and do a reasoning based on combined failure models. So that's the general idea here. But still, there is not necessarily you could also use DDIs without assessing really risk and estimating risk at runtime. So at some point, it could be risk agnostic. But when it comes to dynamic risk management for autonomous systems, then the scope at least includes risk-aware approaches. So let me try to explain what I mean with risk-aware approaches and related to what makes up autonomous systems. They are often described by a cycle called cognitive loop, or the MAPE-K cycle: monitor, analyze, plan, execute, or sense, understand, decide, act, like the SUDA model, which is used, for instance, for the International Program Assuring Autonomy. So they're referring to more or less similar things. And in this cycle, you could also implement risk reasoning, concerning possible action that the autonomous system could perform. And these risks can definitely include safety risks. So there we had, for instance, here a PhD summarizing different ways and approaches to come up with metrics for such risks from Patrick Fade. I linked here PhD. Another one is the situational dynamic risk management approach, so the Sinatra approach from Jan Reich, where we will have later a talk. But from the general concept, you could also relate this to other risks, so that are loss events, which has nothing to do directly with loss of life or injuries, like severe losses concerning environment or financial losses or whatever is valuable. Yeah, so there's really a link also to ethics, thinking about what's really valuable for us. And you could also extend it in the way that you think we not only judge about negative risk, but also have positive risks or chances. Like we have the IESE definitions of risk, which are negative risks in terms of likelihood of harm and severity of this harm, but also we have definitions of risk from ISO, including also positive risks. And you can outweigh maybe some positive risk with some negative risks to make decisions. And this also gives a hint that this control loop would then implement artificial morality. So it would be like the heart of the autonomous system that we have there. And I want to highlight also that this is not, it's somehow related to the control loop, because there you make this reasoning explicit. But in the end, this artificial morality is unavoidable for automating some tasks. So it really depends on the task. And if for this task, it requires you to make moral decisions in some situations, you will definitely implement artificial morality. It's rather a question whether it's implemented in a way that it's traceable and accessible and comprehensible, or whether it's somehow otherwise implemented. But before going into detail into the different implementation approaches, I would like to first clarify some terms, and also this maybe a little bit dangerous term of artificial morality. So first of all, there's no commonly accepted definitions concerning morality or ethics, what it's really related, but I would use the term morality and propose to use it as a set of personal or social standards for good or bad. So yeah, in the sense of morality, morally good or bad. And ethics rather on the reflection of morality. So it's a branch of philosophy. So you could have different kinds of moralities. You could have different morals depending on the social standards or society. But in general, there's not different ethics except for different branches of ethics. And artificial morality would then be like you simulate, human moral capacities. Yeah, this is a little bit related to some definitions of artificial intelligence, referring to the intelligence of humans. But I'm aware that this was maybe not always useful, at least when it comes to standardization and so on, to define it in that way. And that's why I think also the term artificial morality might have some risk in using this definition. But if we refer this like to the morality and you have the artificial morality, then we can say, okay, machine ethics is then the reflection on artificial morality. And I think this topic is really becoming more and more relevant for autonomous systems, even though practitioners might say sometimes, oh no, that's rather a philosophical, not a practical problem. So now coming to artificial morality and the ways how you can implement it. So one way is just implementing in a top-down manner, which relates to generalism, which says that moral is a question of general principles. So you would say, okay, these are the principles, and I will judge about single cases using these principles. So like, yeah, to kill somebody is bad, it's a principle, and then you would judge about it, and then you say, yeah, depending, there are some corner cases and some exceptions because maybe you want to defend yourself and so on. The other approach would be bottom up and saying, okay, you can derive only the principles from single cases, which is a little bit related to AI and how you could maybe then use AI to learn the moral principles that you have. But the input would be the single cases. But still you could say it's generalism because you say there are those principles. Another thing would be that you say they are not such principles. It's related to particularism, where you say moral is rather relates to judgment about concrete cases. You can have a collection of cases, but not principles, or you can have something in between where you say it's only a rule of thumb. And the last approach is then a mixture between bottom up and top down, where you say, okay, maybe I start with some principles to judge about cases, but then I will find out that these principles do not hold for some cases, and therefore I will adapt it. So this approach is then also referred to as reflective equilibrium, to reach a balance between these two ways of implementation. And for really critical decisions, I would say it's at least preferred, for critical decision making, to have a top-down approach to make it accessible and assurable that what your system is doing is in line with something where you generally agreed on. And this raises a little bit the question, what are suitable principles for moral behavior? And here also we have in general 3 ways. And they are also related to moral philosophy, which with a long history. And just to give you an example of a moral principle from Immanuel Kant, he says, act only on that maxim whereby you can at the same time will that it should become a universal law. And this is one principle, but there are many other principles. And if you want to structure these kinds of principles, then you can say, okay, some of them, they are rather related to the motivation, saying, okay, that's depending on how a human is motivated, you would rather judge that it's morally good or wrong. Then you could say it's related to the action, more or less. And the other one, or the last one, would say it depends on the consequences of the action. So this is a rough classification, and there are areas like virtue ethics, deontological ethics, and theological ethics, where the biggest branch here is utilitarianism, where you say, okay, you outweigh and think about different pros and cons. And I would say these theories, you always have to keep in mind that they are made for human behavior. Yeah. So it's not easy and straightforward to apply them to autonomous systems because, for instance, what's the motivation of autonomous systems? Yeah, it's of an autonomous system. But nevertheless, I see some similarities if I look at upcoming approaches and also discussions. And I'm not an expert in philosophy and ethics, but I think it's at least worth that we as engineers need to consider and evolve as experts in this field when we come up with approaches like responsibility sensitive safety model, because at least I see there's some link to deontological approach. Yeah, because it defines few rules saying these are the safe actions. And these rules, for instance, you could take as top-level safety goals and realize these safety goals with conditional safety certificates. Would be one approach. If you have a rule for the safe distance, for instance, and then you say it depends on what I currently have available in terms of sensoring and so on to measure a safe distance, and you have a concrete rule, what it defines, what it is a safe distance. Another thing would be rather here the Sinatra approach, which focuses really on the consequences and try to predict what will happen in the future and then make judgments about the possible actions based on the consequences. So this is rather a consequence-based related approach. And I want to now look a little bit on the consequences approach and also make clear that it's not about or not limited to situation dilemma, where I would agree that this trolley problems, so to say, they are not maybe the most practical problems. Because if you have these approaches, or let me explain this picture first, then you have certain consequences. So you have different actions that you can choose to transform a certain situation in a future situation, or philosophers say a certain current world in a future world. And then you can judge about what is in this future world. Maybe you have an accident or different kinds of accidents, and then you have to choose. But here it's certain that you will end here. But another thing is, if you have a certain action, you can take this action, but then you don't know how what will happen, because maybe the behavior of other participants, traffic participants, is not under your control. And then you have, with certain different likelihoods, you end up in different situations. So you act under risk, and then you can try to make a decision under risk, which is really a challenging thing, because it is somehow a simplification at some point. And then you can have the case where the probabilities are known, and then you can also have the case where the probabilities are unknown. You know that there are some likelihoods, but you just don't know them. So these are, in general, the situations that might occur. And to make this not too abstract, this approach, I want to give you an example in context of automated driving. So just imagine that this vehicle is your ego vehicle, and this option here, phi 1, how to act, would also include whether you maybe use follow straight forward, and then if you accelerate, decelerate, what you do in general. So these are the options that you have. And depending if you say, okay, I take one option, I go straight away, I keep my speed, then there is some kind of likelihood maybe that the other one will steer in this direction. You could also make assumptions that this likelihood is 0. but still you have maybe another assumption concerning the likelihood that it will go straight away. Similarly, you have another situation where you drive here, bypass another vehicle, and then there is a likelihood maybe that there's a bicyclist, which then will here come out, and you could have a collision. So here the probability refers to that having here a cyclist that just jumps in or drives in front of or passes a street here. And then you can also think about maybe you could have the sensoring to distinguish between different road users and also take into account a possible delta speed of different collisions. And then you already run in the question, okay, which kind of accidents are preferred with which delta speed and type of road users and so on. And that's actually a discussion that we had at the at another workshop at the DATE conference, where Simon Burton also noted, okay, this now we've reached a point we maybe have not enough philosophers in our round to continue the discussion, but just wanted to highlight that these are really coming up, I would say, practical problems here. So now let me summarize a little bit the current status, what we have, and also maybe some two branches of approaches. So one approach is these modular safety cases, dynamic composability of safety guarantee demand reasoning and so on, and also the interoperability concerning confidence in claims and in exchanged information. And the other branch is a little bit these risk control loops that we have, where we also have this artificial morality concerning decision making. And I would assume maybe in a first next step from a research roadmap, it might make sense to also think about hierarchical control loops. So you have this as different levels. You have different cyber physical systems are optimizing risk or making risk decisions based on their local scope. But then you have a higher level risk management on which controls then and gives control output to these modular risk control loops. And then if we implement these hierarchical risk control loops, then you have to exchange information, and the confidence in the information will be highly relevant depending on the magnitude of risk that you want to control. And there you can take advantage of the other approaches here and that give you the confidence interoperability. And I would say, I think from the roadmap, also from the roadmap of autonomous systems, various roadmaps that I've seen, we might first have roadmaps for within smart manufacturing, like an adaptable factory and so on, or smart grip or other domains. And also from the interoperability perspective, it might be that we first have interoperability within these domains, but in long term, we might have these domains will grow together. Maybe in a smart city, you connect the smart energy grid system with the smart mobility, and then we come up with a risk control across domains. So this could be a higher level vision for dynamic risk management approaches. So these are in general my thoughts on this approaches for dynamic risk management, also a little bit of my perspective of previous work where I've been involved. Thank you very much for your interest. And now I'm also happy to comment on some questions, because we still have some time